right, let's share that. Just actually give me 2 seconds, guys. I'm just going to go grab my water bottle, and I will be right back.
Radio check, please.
We hear you loud and clear.
Thank you.
And just a housekeeping item, guys. Make sure that you guys are on a push to talk or have your mic muted, or both if you want to make double check. But just to avoid having background noise.
Great, thank you.
Will do.
He's coming back in a second.
All right, so let's see who's here today. All right, well, I expected a smaller crowd since I had to postpone it this week, but good to see everybody here nonetheless. How's everybody doing today?
Great, how are you?
Great.
Good, good. All right, good week, everybody. All right, so welcome to week 3 of our VATSTAR Ground School. Again, we're going to do kind of the same format as last week. So if you have a question, interrupt me as I'm speaking. I'm okay with that if you have something that's pertaining to the topic. And I might call out on some of you guys, and we'll kind of discuss things as we go. All right, sound good, everybody?
Sounds good.
All right,
Good.
cool. All right, so today it's actually going to be a pretty short lesson today. I don't think we'll go over half an hour. This was one of the smaller units that we had. But today's lessons focus on flight instruments and how to interpret them, how they're used. So the main sections we're going to go over: airspeed, altitudes, altimeter settings, vertical speed indicator, the attitude indicator, turn coordinator, heading indicator, magnetic compass, some electronic instruments, which we'll slightly talk about them. We're going to talk about some of the instrument errors and upset recoveries and how you can perform that using your instruments. All right, so let's move on. So this slide you might recognize from last week if you're here. We're just going to go over briefly again. So what we have here is an airspeed indicator, and for the P1 you should know that there are proper airspeeds to climb out, land, and to perform stalls at. So VA, and the V stands for velocity. So VA is what we call maneuvering speed, and that's the speed which you should do your maneuvers at. It's not listed on this airspeed indicator, but it will be listed in your POH, your Pilot's Operating Handbook. For example, a Piper Arrow at max weight is 118 knots. That's the maneuvering speed. Maneuvering speed does change with weight. So if you're lighter, your maneuvering speed is actually going to be lower. If you're heavier, your maneuvering speed is going to be higher. Vx is something that's velocity x, and that's the best angle of climb speed. So you'd use that when you're taking off out of a short field, and that gets you the greatest climb rate over the shortest distance. VUI is something you just use as a normal climb out of a regular runway. That's the best rate of climb speed, and that gives you the most altitude over a period of time. VSO is the stall speed in a specified configuration. We could say landing configuration. VS is the stall speed in a clean configuration. VNE is the never exceed speed. So if you see this red line here, and I'm going to go ahead and turn the pointer on, this red line here, that is VNE, and that stands for never exceed. VNO is the speed here, and basically you want to stay below this in normal operations. You can proceed into this yellow arc, we call this the caution range, but only in smooth air. And finally, VFE is the maximum flaps extended speed, and that is indicated here. This is a 152 indicator, and the max flaps extended speed in the 152 is 85 knots, and that indicates the airspeed at which you can basically dump 100% flaps without risking damage to the airplane. Now, one thing that I did mention last week is on some airplanes, and that's why this is double starred, on some airplanes, you can actually lower a certain amount of flaps above that airspeed. So the 172, for example, Cessna 172, you can actually put 10 degrees of flaps out up to and below 110 knots. It's not indicated anywhere on the airspeed indicator, but it is listed in the pilot's operating handbook. Does that make sense to everybody?
Yes,
Yep.
sir.
All right,
Yep.
cool. Let's keep it going. Keep this freight train rolling. All right, so we're talking about the airspeed indicator a little bit. And aircraft have three types of airspeed. You have indicated airspeed, true airspeed, and calibrated airspeed. Now, for our purposes, you really only have to know indicated and true airspeed. You're not going to have to worry about calibrated airspeed because you're not in a real airplane. Um, but let me call on somebody here. So Emerson, I know you participated a little bit last week. So what do you think true airspeed means? Like when I say true airspeed, do you have any idea what maybe that means?
I believe is the indicated airspeed, but corrected some errors. Or is
Okay.
the yeah?
So close. You actually were talking about what you're talking about is actually calibrated airspeed, and I have that up there. And calibrated airspeed is corrected for errors. Now you are correct. You can get true airspeed from indicated airspeed. So true airspeed is your indicated airspeed corrected for temperature and pressure altitude because as you go up, the air gets thinner and your airspeed indicator might read lower or not as accurately as it would at sea level. So true airspeed we can think of is the speed you're moving in relation to the air. So that's actually your true airspeed. It's the true speed at which you're moving through the air. Indicated airspeed is simply, and this is all you have to know, indicated airspeed is literally what is read on the airspeed indicator. Does that make sense? So true airspeed is really what's important for calculating, fuel burn and distance and times. Indicated airspeed is simply just what is on the dial.
I have a question.
Sure.
So what's the difference between true airspeed and ground speed?
Okay, so ground speed is simply the speed you're moving over the ground. Now, what you have to remember is the air that you're flying in is moving, right? So that we call that wind, right? So the air might be moving at 10 knots or 10 miles an hour, right? So you could be moving at, let's say you're doing 100 knots true airspeed. So you're moving through the air at 100 knots. But if you're moving with the air, that air is also moving at 10 knots or 10, let's say 10 knots. So your ground speed is actually going to be 110 knots because you're moving through the air at 100 knots and you're also being pushed with the air at 10 knots. So you're going to be combining those two and you get 110 knots. Now, let's say you're going the other way and the air is going against you. You're still doing 100 knots through the air, but that 10 knots is moving against you. So you're only doing 90 knots over the ground. Does that kind of make sense?
Yes, what I understand is that um, if you're moving through the air on your ground speed, uh, it could be affected by a tailwind or a headwind.
Exactly.
So
And that's what we say when we say that we're moving either with the air, we're getting pushed by the air with a tailwind, or we're going into the air with a headwind. It's how you're moving in relation to the air mass, because you have to remember the air you're flying through is a fluid and it's moving over the surface of the earth.
Do any of the instruments actually show you true airspeed, or do you have to post-calculate that?
You can. So on some airspeed indicators, you can actually adjust. There's a little dial on the bottom left of the airspeed indicator. And what you can do is you can actually take that and you can put in the temperature at the altitude which you're at, and that will actually read out true airspeed. Now, jets and things like that, the 737 will give you true airspeed. It'll be usually at the bottom of the PFD. It'll say TAS, TAS, and that's your true airspeed. But what's actually shown on like the tape is your indicated airspeed. But it will show you the true airspeed on there on a lot of the bigger airplanes. It'll do it for you.
And under ATC control, are you supposed to be talking indicated airspeed at all times, or do you
Indicated.
what
Yep.
speed?
So when
Okay.
ATC tells you, "Hey, fly 180 knots," they're telling you indicated.
And another quick question.
Yep.
To calculate ETA, you use true airspeed or ground speed?
ETA, you want to use ground speed because that's the speed which you're moving in relation to the Earth. So that's what's critical.
Awesome.
I have a question. Internet is more relevant in terms of flying compared to other speed types, right? Because that's what determines your flight handling as well, right?
You're a little broken up. You're coming in a little broken. I heard something about something that's more relevant.
Sorry, indicated airspeed is more relevant to your flight dynamics compared to other types, right?
Yes. Yeah. Okay. So I'll explain it like this. So if you're at let's say an airplane stalls at 55 knots, right? The airplane will perform according to indicated airspeeds because the airspeed indicator is showing basically what the airplane thinks it's at. So the airplane will perform according to the airspeed indicator. If you stall at 55 knots, you will always stall at 55 knots indicated airspeed. It doesn't matter what the true airspeed is. So when we talk about limitations, like we were talking about in the previous slide, um, VNE is always indicated airspeed. VNO is always indicated airspeed. VFE is always at indicated airspeed.
Because 100 altitude are relative to the ground will be faster.
I'm sorry again. It's coming in really really broken.
Can you hear me now?
Can you type the question? Because I'm having a lot of. I don't know if anybody else is having a problem hearing you.
Sorry, I'm currently driving. If you can hear me better like this, I'm assuming that 100 our actual stall speed is going to be faster, right?
It's coming in really broken. I'm sorry. It just kind of sounds all like mushed together. Can any of you other guys hear him at all?
No, it's very broken.
A lot of stat.
If you type the question for me, I'll answer it towards the end. Yeah, if you can type it for me. But let's move on. All right. So we're gonna move to altitudes now, and I'm realizing now that I actually forgot to include a picture of an altimeter, or I might have, but I'll see when we get. I think it's the next slide. But there are four main types of altitude that you're going to need to know. They're technically five, but I only put four in here. First of all, indicated altitude, and that is the altitude which is on your altimeter, and that is in relation to sea level. So we call that MSL. So when we're at 1,000 feet and we have the altimeter set correctly, we're at 1,000 feet MSL. So we're at 1,000 feet above sea level, and that appears on your altimeter when you set it correctly. And now another thing, and this is going to sound a little complicated, is pressure altitude. Now, do you guys know what standard pressure setting is? The standard altimeter setting? Have you guys heard that before?
2992.
Yep.
Right, and you guys know why we have that?
Yeah,
sorry,
go ahead.
is that the pressure done at sea level? Atmospheric pressure at sea level?
No. So the reason we have it actually is so we can have basically an international standard when we're flying above transition level. So the atmosphere is made up of different pressure differentials. So you find different pressure at different sections. So 2992 or 29.92 inches of mercury in pressure is what we refer to as standard pressure. That way, when we're all above transition altitude, we all fly basically at the same on the same altimeter setting, right? So it doesn't matter where we are. If we were, within 100 feet of each other, if air traffic control puts one of us at 1,000 feet and one of us at 2,000 feet, there's no risk of collision. And 29.92 is also a standard atmosphere, and that's set by scientists, and they refer to 29.92 inches of mercury as a standard atmosphere. And that equivalent in hectopascals is 1013. So when they say QNH 1013 or altimeter 2992, that is a standard atmosphere. And you will always set your altimeter to that above in the U.S. at least 18,000 feet. It changes in other countries, but in the U.S. 18,000 feet. You set your altimeter to 29.92. But we're going to talk about this in a second with a diagram. When you have when they're saying pressure altitude, they're showing that is your altitude in relation to what they call this standard datum plane. And that's basically the level where the air pressure is 29.92 inches of mercury. And I have a little graph in a section that's going to show you and make it a little more easy to understand. But density altitude is that pressure altitude corrected for non-standard temperatures. So if we're, pressure altitude is 29.92, but it's also at a certain temperature. It's at 59 degrees Fahrenheit, 15 degrees Celsius. So when that temperature changes, you get density altitude. And that is that pressure altitude corrected for non-standard temperature. And lastly, absolute altitude, that is simply your height above ground level. So I know it's a little confusing. It's about to get a whole lot simpler. Here's a little graph that explains it. So absolute altitude is your height above ground level, and that is that green arrow here. Now that true altitude that we talked about, or indicated altitude, is your height above sea level. And finally, pressure altitude is, think there's this imaginary plane where the pressure is always 29.92. That is your altitude in relation to this plane. But what's important to remember is because the atmosphere is always changing pressure, this plane, this datum or standard datum plane is actually moving. So one day it might be actually underneath the ground, but as air pressure changes, that datum plane might actually be higher than the ground level. It just depends on the atmospheric conditions. Does that kind of make sense to everybody?
Yep.
Yes.
Yes.
So you don't have to worry about pressure altitude too much. You're going to really be concerned about your true altitude or indicated altitude, because that's what air traffic control is going to have you use. So, altimeter settings. Before departure, it's critical that you acquire the local altimeter setting because air traffic control needs you to have that setting so you have safe separation. But it's also going to guarantee that your altimeter is set correctly, so it's showing your altitude in mean sea level, your height above sea level. So, on the ATIS, that's one way you can get your local altimeter setting. Does anybody have an idea of how else you might be able to correctly set the altimeter?
If
I
you know
do.
the airport elevation.
Yes.
Yeah, exactly. Yeah. So if you actually can't get your altimeter setting, just set it to your field elevation. And you'll notice if you set it to your field elevation, there's this little window here, and this is actually how you set your altimeter setting. So right now it looks like it's set to, actually there's no arrow here, so you can't actually set this. But this is your altimeter setting in inches of mercury. So this is 29.60 inches of mercury is this dash line here. This is 29.70, 29.80. But if you set this to your field elevation, you'll actually have a pretty good gauge of what the actual atmospheric pressure is for your location. So yeah, if you can't get your altimeter setting from the ATIS, set it to the field elevation, and that will pretty much keep you in line for your location. But by acquiring that altimeter setting, you're making sure your altimeter is accurate and reads the correct altitude in relation to sea level. Now, like I said in the last slide, above 18,000 feet in the United States, which is what we call transition altitude or transition level, aircraft use an altimeter setting of 29.92 inches of mercury or 1013 hectopascals in order to ensure they are guaranteed separation. Does that make sense to everybody?
Yes.
Yep.
Does everybody
Yes.
here know how to read an altimeter? If you don't, speak up because I want to make sure you know and I'll explain it to you. All right, I guess that's everybody. But for the people watching on the video later, if you don't, I'll explain it anyway. So what we have here, and I can tell you instantly that this altimeter is at 14,000 feet. And you might be asking, well, how do you know that? Well, I can tell because of the way that the arrows are aligned. So this big diamond here, that indicates your altitude in thousands of feet. So I know I'm at least 4,000 feet. This big thin line indicates your altitude in hundreds of feet. So it's at a 0, so I know I'm at an even 4,000. Well, you might be asking, well, how did I know I'm at 14,000 and not 4,000? Well, if I was at 4,000, this triangle here would actually be below the 1. So this triangle indicates the altitude in tens of thousands of feet. So I know I'm at least 10,000 feet. I'm at least 4,000 feet, so I can combine those two. I'm 14,000 feet. And I know I have no hundreds of feet, so I'm at an even 14 because I'm at least 10,000. 14,000 feet. I hope that makes sense to everybody on the YouTube video. Please comment if you have any issues with that.
So why doesn't the triangle line up on the 4?
Which triangle?
The big triangle, wouldn't it be on the second hash mark past the 1?
It should be. They're not always calibrated perfectly. It's less than 5, so I know it's close enough, but I know that I'm more than 10,000 feet at the very least. So that could be an instrument error, but I know that I'm at least above 10,000 feet, and I'm at least 4,000 above 10,000, and I'm at an even number, so I know 14,000.
Yeah, it seems like you should be able to look at that triangle alone and tell where you are.
Right. All right. So, vertical speed indicator. Vertical speed indicator is designed to indicate your rate of climb or descent, and it's usually at the bottom right of the 6-pack of instruments, right next to your directional gyro. And if it is indicating a climb or descent on the ground, right, we're going to talk about the error of it now. If it's indicating a climb or descent on the ground, note the error and apply it to readings in flight. So sometimes, and my airplane it does this, on the ground it'll actually read 100 feet. So I have to know that 0 is actually 100 feet, and 100 feet is actually 100 feet is actually 0 feet. 200 feet is actually 100 feet. 300 feet is actually 200 feet. It just gets a little confusing, and I actually know that when it's 0, I'm descending at 100 feet per minute. So when they say take that error from the ground, just apply it in flight. And each one of these hash marks is your ascent or descent rate in hundreds of feet per minute. So this hash mark is 100, 200, 300, 400, 500, all the way up to 1,000, and then 2,000. And you can tell it if you're climbing because it'll be up, or if you're descending because it'll be down. Does everybody kind of get that concept of the instrument?
Yep.
Certainly. Yep. Yes.
Cool. All right. Now we're going to talk about electric versus vacuum instruments. Aircraft instruments are typically powered by either electricity or the vacuum pump of the airplane. Now, the attitude indicator, right, which is this horizon looking instrument here that shows you in relation to the horizon, is actually powered by a vacuum, and a lot of people don't know that. And the same thing with your heading indicator, or another name for it is directional gyro, that's actually powered by a vacuum. And what happens is you have air being sucked in through the air filter, and it actually goes through the gauge. And what happens when it proceeds through that gauge is it spins a gyroscope. Now, we talked about gyroscopic precession in the second week. And that, does anybody remember the principles of gyroscopes that we talked about last week?
I think it was rigidity in space.
Yes, yeah, exactly. Rigidity in space. And rigidity in space states that a gyroscope will basically maintain its position because it's a rapidly spinning object. So if you tried to basically apply an outside force on it, it would resist that force because of its rotation. And it maintains its position on an X, Y, and Z axis at all times. So that's the principle of how these instruments work. But the vacuum pump creates suction and actually spins those instruments and creates rigidity in space. And those are the principles on which these instruments operate. So that's what we say when something's vacuum powered. Now we can actually talk about, I don't have it on this page, but the turn coordinator, which we're going to talk about in a little bit, is actually a gyroscope, but it's not powered by that vacuum pump. It's actually powered with electricity, and a motor will actually spin the gyroscope up. And that is a fail-safe in case you lose that vacuum system. So now that we talked about how this attitude indicator is powered, let's talk about how it works. The attitude indicator shows the airplane's offset and rotation in relation to the Earth's natural horizon. So when you're on the ground, it should be reading perfectly level because you're on the ground and you're basically pointed right at the horizon. If you're climbing, it's actually going to indicate up into the sky. If you're descending, it's going to indicate down to the ground. If you're in a bank, it's going to indicate a roll left or right. And these instruments are able to achieve this by using that gyroscope that we talked about and their principle of rigidity in space. Now, let's show you what the inside of this instrument actually looks like. So here on this vertical axis here, you actually have the gyroscope spinning around and around and around. Now what happens is, as you rotate, think that you're actually rotating around this gyroscope. This gyroscope, because it's spinning, is actually always pointing basically up or down. This vertical axis will constantly stay either it'll constantly stay pointed either to the ground or to the sky. So it's basically a perfect vertical line at all times, no matter which way the airplane's oriented. Now, that can get screwed up if you're doing aerobatic maneuvers. No gyroscope is perfect. It does fade over time in its accuracy. But that rigidity in space principle helps keep it upright at all times. So you can think that the instrument's actually moving around the gyroscope. So as the entire instrument moves around the gyroscope, let's say you roll to the right, that gyroscope is going to indicate a roll to the right because it's of the way that it's staying upright and the plane's moving around it. So here you can see that it rotates around this gimbal here to indicate bank, and it rotates around this gimbal here to indicate pitch. And that's how we get those bank indications and pitch indications from the attitude indicator, just because of a gyroscope. Now, there are a couple errors associated. Like I said, gyroscopes aren't perfect. If you do a 180-degree turn, the attitude indicator will actually indicate a climb and a bank in the opposite direction, and we call this the turn error. During acceleration, if you were to ram the power full forward, right, the horizon bar, which is this white bar here, is actually going to indicate a climb. During deceleration, that horizon bar moves up, indicating a descent. And those are just some of the errors we have to remember for when we get to instrument flying. We're not going to go too far more into explanation than what I just told you. But it's good to know them in case you notice something or have questions about it. Anybody have questions about this instrument?
So the only errors are the acceleration errors and deceleration errors, right?
Yep,
And
and,
turning
and
errors.
those are the common errors. Yes, that's the only ones that you're going to have to know.
Okay.
So how,
Sorry, James.
Yep.
So therefore, if you accelerate and the horizon bar moves down and you say that that is an acceleration error, okay,
Right.
does that mean actually that the plane is not climbing, that it is on the same level?
Yes, it's not
of flight?
actually climbing. Yep. It's not actually climbing. The instrument just indicates that you are climbing. You actually haven't changed your relation. It's just because of the force of the acceleration on the gyroscope causes either a change in indication of the pitch.
Okay, so then so then one way to check this is also to look at the altimeter, right?
Yeah,
Because
exactly.
then,
You can look at your vertical speed indicator. That's one way to check if you're
Mhm.
climbing or descending. And that's the whole thing. You have to verify these indications with other instruments, and we call that a cross check. So if we notice
Mhm.
one thing with one instrument, well, hey, we have other instruments that we can use, like in this case with those errors, the vertical speed indicator and the altimeter. We can check to see if we're actually climbing or descending.
Okay, thank you.
No problem.
May I add on that?
Sure.
There's also the fact that your angle of attack might affect whether it's showing climbing or flying straight too, depending on different speeds.
What do you mean?
In certain situations, the nose of the plane might not be aligned with the direction that you're going when you're flying a high angle of attack.
Oh, sure, sure, but that doesn't make the instrument inaccurate. That can just simply mean that you're, pitched upwards, which is, that's
Yeah,
possible in cruise.
yeah.
Obviously, at a slower
Basically,
airspeed, you'll be pitched higher.
yeah, exactly. That's why I was saying the attitude indicator may not always indicate whether you're climbing or not.
Yeah, exactly. It's just in relation to wherever you were. If you were to accelerate, it would indicate a climb based off where it was previously, if that makes sense.
Sure.
Okay. All right. Let's move on. Let's talk about the turn coordinator, which is that backup instrument to that attitude indicator. So, like the attitude indicator, that turn coordinator, like I said, also utilizes a gyroscope, like this. But it's not a vacuum powered gyroscope. It's actually spun up by a motor. And that is just a backup in case we lose that vacuum system. So, this is another instrument we can look at to tell if we're banking. Now you might be asking, well, how do we tell if we're pitching? Well, I'm sorry, I'm forgetting your name. Sergio brought up that you can cross-check your instruments. So in the case where you lose your attitude indicator, you actually use your turn coordinator to tell if you're turning, and your vertical speed indicator and altimeter to tell if you're climbing or descending. But one important thing is a turn coordinator shows an indirect angle of bank. It doesn't tell you what bank angle you're at, like 10 degrees, 20 degrees. It just tells you whether you're banking left or right. And that's because it's a little bit of a less precise instrument, and just the way that it's built, I think electric turn coordinators are a little less efficient. But it will tell you whether you're banking left or right. And a turn coordinator acts as backup, right, in case we lose an attitude indicator. But what is important is no matter your airspeed, the turn coordinator allows you to perform a standard rate turn. And a standard rate turn is 3 degrees per second. So you're changing your heading by 3 degrees every second. And that's regardless of airspeed. Does that make sense to everybody?
Yes.
All right, cool. Let's move on. So, like the attitude indicator, the heading indicator is another vacuum-powered instrument. It's on a different axis, and a vacuum-driven gyroscope creates suction, spins the gyro, and due to rigidity in space, you can indicate your current heading. Now remember, that gyro is basically remaining in a constant position. And like I said, think of you moving around the gyro as the gyro stays stationary. And we can see it's on a different axis here. It's spinning around a lateral axis, we could say, or even a longitudinal axis, but it's not vertical like the attitude indicator was. It's actually horizontal or parallel with the surface of the Earth. And you can see the gimbal rotates around this, and a combination of gears translate that rotation into a rotation in this direction, which indicate your heading. So very similar to the attitude indicator, just a little bit of a different setup, but they're both gyroscopic instruments. Any questions about that?
Yeah, one question.
Mhm.
Is it realistic or is it thinkable that one of those instruments gets broken during the flight?
It is possible, yeah. That does happen. Um, and another thing we can talk about is gyroscopes actually precess. The other concept with gyroscopes is gyroscopic precession. So due to friction and along with precession, this will actually become inaccurate over time. So what you have to do is, you see this adjustment knob here? You can actually adjust this card so it indicates correctly, because over time it will actually drift, and you'll have to realign it with your magnetic compass to ensure that you're flying the correct heading.
What's over time? Is it like an hour, or is it like months, days?
Uh,
What do you mean?
yeah. So by over time, every gyroscope is different, but it's typically between 15 minutes and an hour. Every gyroscope is a little bit different. So the saying among pilots is they either drift all the time or they don't drift at all. Um, it just depends on the quality of the gyroscope. But between 15 minutes and an hour, you will have to reset it and reset the card based onto magnetic heading.
Thanks.
This will not be true in the case of the heading indicators that are electrical on a glass panel.
Okay, so that's going a little bit into a different concept. So those heading indicators actually self-align. Those electric ones are connected to this device called a magnetometer. And it's basically a magnetic compass that's digitally connected, and it realigns itself when it realizes it's at a drift. So we're specifically talking about an analog instrument here. On the glass
Okay.
cockpit, like the G1000, you actually don't have to set it yourself. It'll do it for you.
Okay. Thank
And
you.
as far as I know, G1000s also have a built-in IMU in them, so they're using electronic measurement methods rather than gyroscopes as well.
Yeah, that's correct. They use what's called AHARs.
Can I have a question, please?
Yeah, go ahead.
So this gyroscope seems to be reading at like 45 degrees, like, 45 degrees.
Yeah, that might just be the way that the diagram's set up, because this is actually spinning. So
Right.
that could just be the way that the diagram is set up. But yeah, you got to remember it's spinning around this, and that causes this gimbal rotation, and that gives you an accurate reading on your heading card.
Okay, got it. Thank you.
Awesome. So I talked about how you have to realign it with your magnetic compass. Well, that magnetic compass is the only self-contained. It's actually separate. It's unpowered. It's a self-contained directional instrument in the aircraft. That is, I hate to say this, that is the one instrument that usually never fails. It can, but usually never. The magnetic compass is literally just a compass, like, one that you take out of your pocket and read to see which way is north. And it indicates your direction in relation to magnetic north. So inside the compass, there's actually a magnet that always points north, and again, this little dial spins around that to indicate your heading. However, like everything else, there are errors associated with the magnetic compass, and this device actually has the most errors out of all of them because it's so old school. So this is going to be deep, and if you don't understand, I'll try my best to explain if you have questions. But there are two main errors. One of the errors, which is associated, it's a different error, but it's also referred to as an acceleration error, which we talked about with the attitude indicator. This only happens when you're going east or west. If you accelerate the aircraft when you're going east or west, the magnetic compass will actually indicate a turn to the north, no matter if you're going east or west, even though it has not happened. As you decelerate, if you pull the power back, it'll actually indicate a turn to the south, even though you're not turning to the south. And that's because the magnet inside the compass actually dips when you do that and causes it to think it's turning, but it's really not. Now, the way we remember this is we use this acronym called ANDS, and that stands for accelerate north, decelerate south. And that helps you remember which way the compass turns when you accelerate or decelerate. Does that make sense to everybody?
Yes.
Okay,
Yeah.
cool. All right, so another error is what we call the northerly turning error. Now, this one's going to sound a little ridiculous. You're going to be like, oh, how does an aircraft instrument be this unreliable? Well, it happens. So if you're, let's say you're flying northbound, you're on a 360 heading, which is exactly due north. If you turn to any other heading from north, the compass will actually indicate a turn in the opposite direction. So if you make a left turn from north, let's say you're flying 360 and you turn left to 270, it'll actually initially indicate that you're turning right to like 010 or 020. And it kind of screws with people's heads that the compass does this, but it's just one of the errors because of the way a compass is designed. Now, let's say you're flying south, you're on a 180 heading, which is due south. If you fly to any other heading, the compass will indicate a turn faster than what's actually happening. So if you turn from 180 to 270, which is a right turn, it'll actually think you're turning faster than you actually are. And that's just something that you have to account for. So you might think that you're actually you might have to overshoot your turn to actually end up on the heading you want to be if you're using that magnetic compass for navigation. Does that make sense?
Yes, I have a question.
Sure.
So, for how much time does it indicate the error in both?
Sure. So the way to remember it, right? So let's say, I think the rule of thumb is half of the latitude at which you're at. So let's say you're at 40 degrees north of latitude on the Earth. If you cut that in half, you get 20. So you're at 20 degrees. You can expect that error at 40 degrees north latitude to exist for 20 degrees. So that's kind of the rule of thumb. You half your latitude, and that's how long the error is persistent for. Um, that's a basic explanation I can give you. Um, Does that kind of answer your question?
Yes. So for 20 degrees, it is unreliable.
It's not unreliable. You just have to account for that error. So if you're south and turning to the right, you should overshoot the heading you want to go by 20 degrees because the compass is moving faster. So if it's 20 degrees error and you're turning from 180 to 270, you should actually shoot for 290 degrees on the magnetic compass. And when you stop there, over time, it'll actually drift back to 270 and show you're doing a correct heading of 270 degrees. So that's kind of a way that you can correct for that compass error. When you're turning from the north, you should undershoot by 20 degrees if you were at 40 degrees of latitude. It's a little bit complex. If you want to go research it after, it's not going to be that prevalent in the flight simulator, but it's just a good thing to know again. If we want to talk about it after, we can go into more detail with it.
How well is this modeled in the flight simulator?
In P3D, I know it's actually modeled pretty well. I'm not
May I
too
say
sure about
one thing?
X-Plane. Yeah, sure.
Interesting. There's in the new Microsoft Flight Simulator are exercises for flying, and if you go for your first solo flight, you make exact this experience what James just told us.
Oh, is there a mission where you have to use the magnetic compass?
Yes, indeed.
Oh, okay.
It is a first solo flight.
Oh, wonderful. Well, that if you guys want to go see the error in a sim, he says it's there. So go check that out. All right. I know magnetic compass again, a little confusing, but I can even demonstrate it after the ground school for any of you that are still confused. Oh, we're gonna go back more into instrument errors. So back to airspeed, the altimeter and vertical speed. They actually, believe it or not, they all draw their data from the same sources. Now it's not like digital data; it's physical air. Um, the airspeed indicator uses what's called ram air pressure, which is air being forced into the pitot tube here. We call that ram impact pressure, and compares it to the outside air pressure from the static ports. And that's how you get your indicated airspeed. Now, the altimeter and vertical speed actually just use the static ports. They don't really care about what's coming in from the pitot tube. But they all are connected to the static ports, and the airspeed indicator is also connected to the pitot tube. Now, why is that a problem? Well, if all of a sudden you lose air or this gets blocked, you no longer have airspeed. If this is completely blocked, there's also what we call a drain hole at the bottom of the pitot tube. If both of those are blocked, the airspeed indicator will actually get stuck where it is and act as an altimeter, which is kind of weird. I'll try. I could see if maybe we can demonstrate it in a sim a little bit, but it will actually act as an altimeter, and it's a little bit funky to think that. There's also that drain hole, like I mentioned. If that stays open, the airspeed indicator will just read 0. But if we lose those static ports, you'll actually lose the altimeter and you'll lose the vertical speed indicator. And I have a little diagram here that goes into every single error that could happen. So let's say you have a blocked pitot tube, you'll get 0 airspeed, the altimeter will work, and the VSI will work. If you have a blocked pitot tube and that drain hole that I mentioned is blocked, but you have an open static port, the airspeed indicator will indicate high in a climb, low in a descent. The altimeter works, and the vertical speed indicator works because you still have that static port. If you have a blocked static port but an open pitot tube, the airspeed indicator will actually indicate the opposite. You'll indicate low in a climb and high in a descent. So that's kind of what you would want. You would want it to go low in a climb and high in a descent. This is better for stall avoidance. The altimeter will actually freeze, and the VSI will freeze. Let's say you're using alternate cockpit static air. Now, the air inside the cockpit is actually warmer and typically of a lower pressure. So because of that, your airspeed is going to read high, your altimeter is going to read high, and your vertical speed indicator is actually going to show a climb. Now, one way you can actually get static air and an alternate static, you can actually break the vertical speed indicator, and that will give static air to the system. But your airspeed will read high, your altimeter will read high, and the VSI will actually reverse. It's a little bit of a weird concept, but these are the errors that are associated with that pitot-static system that I just showed you in the last diagram. Does that make sense to everybody?
Yes.
Yeah.
Yes. Yes.
Okay. All right. I think we're coming up on our last slide here. All right. Now, I'm not talking about stalls here. Let's just say that you're flying around and, you accidentally fly into some clouds and you get a little disoriented. Well, let's say you look at your instruments and you realize, whoa, I'm banked 30 degrees and I'm pointing straight at the ground. Or, even worse, actually, that's the worst, but the other thing is, let's say you're banked 20 degrees and you're pointing straight up to the sky. Well, how the hell do you get out of that situation? Well, there's a couple straightforward solutions. If you're pointed down to the ground and bank, it's a three-step process. If you're pointed down, you want to reduce the amount of time that it's going to take until you hit the ground. So pull the power out. You want to unbank the aircraft. So look at your attitude indicator, unbank the aircraft, and then pull back the yoke and level the airplane. And the reason you level the wings first is to reduce uneven load factor on the wings. We talked about load factor in the first week, so I won't go into it. But you want to reduce that uneven load factor on the wings. If you're in a state where you're pointing straight up to the sky and banked, simultaneously add power, apply forward pressure, and level the wings. Now, this is different from recovering from the ground. You want to unroll and level off at the same time because you don't want to end up stalled, because if you stall and you're in instrument conditions, well, that's no good. You're stalled out, you're probably in a spin at that point, and you're going to hit the ground. So you want to get out of a climbing scenario as quickly as possible. Does that make sense?
Yes.
All right.
Yes.
All right. I believe that is all I have for today. So we'll conclude the ground school at this time. If you don't have a question, I will see you hopefully next week. Thanks for coming, and yeah, I'll see you all next week. And if we
Yeah.
have any question takers, go ahead.
James, here, Sergio. Well, this is the first session that I come here, and unfortunately, I missed the other ones. Is there a place where I can take a look at the videos or even the future videos of these sessions?
Yeah, so they're all uploaded to our YouTube channel. Go to YouTube and look up VATSTAR Virtual Pilot Training. Weeks 1 and 2 have been uploaded. You can watch the videos there. And that should keep you up to date with everything. And they will be posted. This is going to be posted. The one next week will be posted.
Or you can go to youtube.vatstar.com.
Okay, thank you.
I didn't even know that. Thank you for that.
It just came up
Oh, okay.
today.
Good. Anybody else? This is a free range right now. Yeah, sure.
From earlier on when I tried to ask about the altitude indicator with how, sorry, not the altitude indicator, the airspeed indicators, indicated airspeed and everything.
Okay.
Would it mean when we're at a higher altitude that our stall speed being higher means that we would also take a longer time coming to a stop when we're landing?
You actually stall at the same indicated airspeed. It doesn't matter what altitude you're at. So if you'll stall at 55 knots at sea level, you'll stall at 55 knots at 18,000 feet.
Sorry, let me make myself clear. I mean, ground speed. It's going to be a higher ground.
Yes.
Lower.
Yes.
Yeah, higher ground speed.
You'll have a higher ground speed because the air's thinner and you're indicating. You will have a higher ground speed. Yes, that's correct, because the air that's coming into the airspeed indicator and over the plane is thinner. But because of that, you're actually flying over the ground faster. So yes, you will have a higher ground speed at a higher altitude.
Okay, so that also means when we're coming in for a landing at a high altitude, our roll-off distance is going to be longer as well.
Exactly. And if you look at a POH, you'll actually see on the takeoff and landing distance that your ground roll will be higher at higher altitudes.
Okay. Thank you.
No problem.
One last question. Will all our future lessons be on Friday? Because the last, this lesson was announced on the events page for last Wednesday.
Yeah, that
And
that was my fault. It should be this Wednesday. I think it's gonna stick to Wednesdays. I just had a family situation. I had to move it to today, so it should be on Wednesday for next week. If that changes again, Edward will make an announcement and let you know. But I'm planning on Wednesday.
okay. So there's no possibility to move to Friday.
Um, I mean, I'm okay with it. I can look into it, and I'll maybe take a poll and see what works as a better day for everybody. So, but it's possible I could move it to Fridays if that works. But I might take a poll and see what day works best for everybody.
Okay, thank you.
No problem.
Okay, thank you.
One last question: are they always at 2100 Zulu time?
Yeah, but it's actually always at 5 p.m. Eastern, but because daylight savings is starting in a couple days or a week, I think Edward knows the exact. It's actually going to move to 2200 Zulu, I think.
So
Okay.
2 weeks.
Yeah, November 1st is the first one, and it's going to be moving up to 2200 after November.
Yep. So that sounds right to me. So it'll be moving to 2200 Zulu. If you need to know the exact time, it's always going to be 5 p.m. Eastern.
Gotcha. That works out for me.
Okay, good to know.
All right.
Okay, so Lepke, thank you for this lesson. Bye-bye.
No problem. Have a
Yeah,
good night.
thank you so much,
Yeah,
Jane. And
No
I'll
problem,
see you
guys.
next week.
I will
Thank
be
you.
happy to see you guys next week.
Yeah, thank you.
Thank you.
Thank
See
you,
next week.
James.
Bye.
Thank you.
Thank you.